Hello and good afternoon. Welcome to this presentation on modeling biosensors with COMSOL. My name is Ross Hubble, and as I'm part of the application support team at our Cambridge UK office. I mainly specialize in the support of chemical and electrochemical applications. In today's presentation, we're going to be exploring why we might be interested in investigating biosensors within a simulation environment and how we can achieve this within COMSOL. I'll then briefly run through the different types of physics we might be interested in investigating in a biosensor before demonstrating their application by building a biosensor model example. And at the end of this presentation, of course, there'll be an opportunity to answer any questions. So what are our motivations when we simulate a biological system? Biosensors are sort of the workhorses of biological analysis. They're often used in medical testing applications, however may also be quite useful in academia, for instance, to help improve the mechanistic understandings of your biological system at a molecular level. These analysis tools are used in countless applications for the detection of biomolecules within fields of pharmaceutical, agriculture, environmental technologies, and food technology. The powerful combination of theory, simulations, and experiments has increased our understanding of molecular level behavior of biological mechanisms and systems, and this knowledge has yielded a myriad of methods for detection of biomolecules in medical applications. Biosensors themselves play significant roles in drug discovery and targeting, microbial and virus detection, gene therapy, and other processes in biotechnology. Through simulation, we can investigate complex systems. It may be difficult or time-consuming when dealing with an experimental system to identify which physical processes are limiting. However, through simulation, these influences can be quantified and identified more rapidly. This is particularly useful when examining the design and optimization of a sensor system. Simulation helps streamline design through reducing the number of physical prototypes you might need to make, and also allows for potentially flawed concepts to be rejected earlier within the design process. So how does COMSOL Multiphysics software fit into the simulation of biological systems? The main advantage of COMSOL Multiphysics is the multiphysics approach, and this allows us to include many different types of physics and many different types of equations, all within a single model and using a common user interface. And this approach is a real advantage for biosensor design, being able to combine heat transport, mass transport, and chemical reaction within a single package. COMSOL offers a great openness and flexibility, which enables the incorporation of your own novel equations or material properties into your model and helps develop a high fidelity representation of your system. A further feature COMSOL offers is the ability to turn models into apps through the application builder. The application builder enables you to, as the expert simulation user, to create your own models and then deploy it as an app with your own user interface. Apps can be set up to display results, and input can be restricted to just a handful of parameters, which makes using the app a lot easier for colleagues who are perhaps slightly less experienced with simulation software. Today's demonstration model for the biosensor is available within the application gallery of our website and contains a pre-built version of an app if you are interested in exploring this in greater detail. The multiphysics approach itself is a real advantage in biosensors where our multiple physics are being combined together into one device. For instance, fluid flow physics is important if we're looking at lab-on-chip devices. Accurate electromagnetic modeling is going to be important if we're simulating impedance sensing, or in the modeling of biological separations within an electric field, such as electrophoresis. We have here an industrial application example where Harvey Buck of Roche Diagnostics has used COMSOL to examine their glucose test strips. So in analyzing the mechanical and electrical and chemical physics together within one model. It's helped predict the sensitivity to cell fraction within the test strip. Glucose monitoring systems demonstrate one kind of biosensor design which benefits from a multiphysics approach. Through combining these mechanical, chemical, and electrical physics into a single model, we can get a higher fidelity representation of the system. And then this in turn allows us for making better optimizations and better design choices when developing our biosensor. The underpinning principles of chemical simulation are the conservation laws for mass, momentum, and energy. With chemical simulation, we'll usually be interested in how fast one species reacts to become another, and within COMSOL, these physics can be modeled and coupled together using the different physics interfaces. Now, these physics interfaces are how COMSOL refers to the different physical equations which underpin the system. So these physics interfaces package up different equations which describe different physical systems or phenomena, and the pre-built physics interfaces help enable easier specification of your physics for each application. They group together the relevant domain and boundary conditions all within a single node. So for instance, here we have the laminar flow interface, and this has nodes for inlet flow conditions of velocity and pressure, or the transport of diluted species interfaces has nodes to describe species flux, concentrations, or reactions, to name a few. These interfaces also contain default nodes which are essential to each simulation. For example, the transport properties node for transport diluted species is used to specify the diffusivities of the model species and the velocity field that they experience. And these default nodes are automatically included within each physics interface to help save time when setting up your model. So let's briefly discuss the different capabilities for species transport within the chemical reaction engineering module. The list here represents the physics interfaces available with the chemical reaction engineering module and some of the relevant functionality from the CFD module. The interfaces are separated into distinct themes, so fluid flow, heat transport, and chemical species transport. So aligning with our previous separation of the conservation laws. At the top here, we have mass transport and reactions. We have transport of concentrated species and transport of diluted species. These are used to determine the diffusive movement of species and may be coupled with the fluid flow interfaces to incorporate an accurate representation of the convection. Migration can also be added to include the influence of an electric field on the transport of your ions. We also have momentum transport. So this is going to be representing our fluid flow. In COMSOL's chemical reaction engineering interfaces, we have laminar flow, reacting flow, and porous media flow included, which is important for modeling porous domains you might have within a chemical reactor or perhaps within your sensors. With the addition of the CFD module, you also obtain the capabilities to model turbulent and multi-phase flows. Heat transport can be a key element in many chemical processes. So reaction rates are often sensitive to temperature, and reactions may generate heat that require or require cooling. Hence, the capability to model thermal transport within your system is quite important. The chemical reaction engineering module contains the physics interfaces necessary to describe both convective and conductive heat transport in both the free domain and the porous media. Finally, we also have the reaction engineering interface here, and this provides a means to describe to define the reactions and compute the behavior for idealized reactor models, such as a perfectly mixed batch reactor or a plug flow reactor. And this can help you examine the kinetic behavior of systems under ideal conditions. The reaction engineering interface itself is a zero-dimensional physics interface, and is used to help compute the mass and energy balance equations for describing an ideal reactor system. This assumes a perfect and well-mixed reactor. And while this is not the case for our biosensor, it can be used to quickly generate the required physics interfaces in a space-dependent model. Once we have the reactions defined in the reaction engineering interface, a 1D, 2D, or 3D space-dependent model can be generated from it with the related reactions and transport properties already pre-populated with the necessary reaction data. So this simplifies the model setup a little bit and can help when dealing with very complex reaction systems, leaving you with only a few additional boundary conditions to specify, for instance, such as the inlet velocity if you have a fluid flow problem. So here we have a few more general highlights of the types of physics we might apply when examining a biological application. We could use heat transfer to investigate the influence of metabolic heating, or examine an application such as tumor ablation. We might also perhaps use acoustics to model ultrasound-based diagnostic technology, or mechanics to design implants, or examine the stresses in biological materials. We'll now discuss a little bit more about some of the key physics when we're dealing with our chemical reactions before building our biosensor model. In terms of when to use each transport interface, the transport of diluted species interface is appropriate when the solute interacts only with our solvent molecules. So this model uses Fick's law to describe the flux of species and is generally applicable only to dilute species that is modeling species with a low mole fraction relative to the solvent. So this is quite common if you're looking at something dissolved within a liquid such as water. For more complex multi-component systems where each species has a significant interaction with one another, it's often more appropriate to use a multi-component transform model. And COMSOL offers the Maxwell-Stefan or the mixture average transform models to help describe this. So the Knudsen and dusty gas models are also included. And this is an approach more commonly used if you're looking at gas phase systems, but could be used if you are looking at quite complex mixtures. For surface reactions, so surface reactions are going to be very important within our biosensor, as well as sort of more general heterogeneous reactions such as reactions on catalytic surfaces. So instead of a bulk consumption rate across the domain, as we would have with say our transport of diluted species just with a chemical reaction within the fluid, we now have to describe our rate on the surface. And this can be described as a boundary flux acting as a source or a sink within the model. And at the surface, concentration gradients will develop to match the flux and the demand of the species at the surface. In mass transfer limited systems, we might also observe quite significant concentration gradients, and this will be then where we can then investigate whether mass transport limitation will reduce our observed reaction rate. And this can be quite useful when simulating the system to investigate this. It's quite difficult to determine this experimentally. So here we have a highlight of some of our electrochemical physics interfaces as well, which may be useful for some bioelectrochemical sensors. We break these down into 3 different current distribution interfaces. So our primary and secondary current distribution interfaces take an ohmic description of the electrolyte resistance. So it just describes the current distribution and the potential within the electrolyte using Ohm's law. So the primary current distribution relates the electrode and the electrolyte potentials by the equilibrium electrode potential, whilst the secondary current distribution also includes the influence of electrochemical kinetics. If we're going to a further level of complexity, we can use the tertiary current distribution interface to then consider the movement of ions within the electrolyte explicitly using the Nernst-Planck equations to describe the transport of both charged and neutral species. For sensor systems, electroanalysis can be a convenient interface to use as this models systems where there are no significant potential gradients within the electrolyte, and just allows you to consider the mass transport and the electrokinetics. And this can be quite useful if we're looking at biosensors, for example, a glucose sensor, and we have a good example of that within our application library. So moving on to looking at the biosensor in a little bit more detail, the schematic here shows one possible arrangement for our biosensor. Here we have an enzyme immobilized on our pillars, well, on our detector pillars, and we have a flow coming in from the left to the right. The enzymes immobilized and attached on our gold surfaces here, and because it's an enzyme, it can only attach to the biomolecules which we're interested in detecting. So in this biosensor, the biomolecules are absorbed onto our enzyme-coated pillars, where they can then be measured, for example, by another detection method. So for instance, we might have fluorescent detection. Enzymes, in this case, are very good as receptors because they can only then attach to our biomolecule of interest or a very specific group of molecules. And in our reaction, we're going to have our biomolecule attaching to our enzyme, and then we're going to have a second reaction where the biomolecule is quenched, and that will then be represented as perhaps our signal being weakened, or this quenched biomolecule no longer fluorescing. So if we look at the full geometry here, we can see that it has two symmetry planes which can be used to reduce the simulated system size. And by reducing the size of the system and using symmetry boundary conditions, this will reduce the number of mesh elements required and then reduce the computational requirements for our model. And this can then lead to a faster simulation, and in using symmetry, also then not losing any fidelity in our model, because we can actually reconstruct the full geometry from our symmetry planes in the post-processing, just using mirrored data sets. The model itself, we're going to be using three main physics interfaces to describe the reactions. So we're going to have flow represented using laminar flow. We're going to have our reactions represented using the transport and diluted species and the surface reactions, as well as our diffusion process. The laminar flow interface, we're going to describe the fluid flow within the channel, solving the Navier-Stokes equations. The fluid properties we're going to assume are just going to be taken from water, and we're going to have a inlet flow rate of 0.2 millimeters per second in the left-hand side, and then we're going to have our flow at the outlet with 0 gauge pressure, and then these symmetry planes are going to be used to just reduce the geometry down. So since the concentration of our biomolecule in the fluid is going to be assumed to be dilute, we're going to be representing this using transport diluted species, which uses Fick's law to describe our diffusive and convective transport. The inlet concentration here is going to be a time-dependent Gaussian pulse with anything which is unreacted after passing our pillars leaving our outlet here. At the surface of our pillars, we're going to have two reactions happening. So we're going to have our P, our biomolecule, reacting and absorbing and desorbing onto our surface. And we're also going to have the adsorbed species being quenched by our quenching reaction, which is our second reaction here. Okay, so let's move on to COMSOL and see how we can build this model up. So opening COMSOL, we are presented with the new screen to start with. The two options are either to use the blank model or the model wizard button here. And we always recommend to start with the model wizard, since it will ask us a few questions and pre-populate our model builder tree with the required physics interfaces. The model wizard is going to ask us a series of questions about the model to ensure that we start off with the right physics, with the right studies, and any couplings between the physics. So here we're going to select our 3D space dimension to represent the biosensor. We recommend using the lowest space dimension possible for your application, as this reduces the memory requirements and leads to a faster simulation. For many chemical reaction problems, a reactor system may be tubular, and this may then benefit from something like a 2D axisymmetric simulation. But in this case, we're going to have a 3D system for our biosensor. The physics selection screen here presents us with an array of different physics interfaces, and each of these will be grouped by the types of physics to which they're applied to. So we here have our chemical species transport and our fluid flow. And information on each of the physics interfaces and what they're capable of is given on our right-hand pane here. So let's select the transport diluted species and add that in. So with this, we have one species, and we're going to have our biomolecule be called P. So we'll have our concentration of P represented by C_P. We now need to add in our surface reactions. So we can select our surface reactions interface here and select add. And we have two surface species in this case. So we just type in 2 here, and then we go call them CSP and CSQ. So once we've defined our reaction physics, we can also add in our fluid flow physics. So in this case, we're just going to take our laminar flow interface to describe our Navier-Stokes equations. So selecting study, this screen gives us the study options, and this list is not exhaustive of all of the possible studies in COMSOL. It is just the studies which are compatible with our selected physics interfaces. So for this one, we're going to have a time-dependent study to represent the time dependence of our system. So we're now presented with the COMSOL desktop. So the main windows to look out for here are our model builder tree. And this gives us a hierarchical overview of our model structure. The settings pane here is where we can then enter values and parameters and customize our model. And then the graphics pane here will give us a view of the geometry and make it easier to select our domain and boundary conditions. So what we recommend doing with the model builder tree is always start at the top and then work your way down, as it's designed to have a logical workflow for the system. So we'll start with our parameters and then we'll load in some parameters for our model. So what we have here are just some rate constant parameters, our diffusion coefficient, our inlet velocity, some geometric parameters for our system, which we don't need to worry about too much. And then we have some parameters about our inlet concentration and then our solution times. If we move on down, I'm going to also define some variables. So parameters are going to be constant global values, but we can also custom define our variables, which can have time dependence or spatial dependence. So adding in our variables, we have a definition of our inlet concentration, which changes with time, our reaction rate for our absorption process using our kinetic parameters from our parameters list, our desorption rate, and then our quenching rate, so just our kinetics there. And these are using the dependent variables from our physics interface here. So this is using the surface concentration of our species P, and this is using the surface concentration of P and Q there. And then this one is using the vacancies on our site and on our pillars, and then the concentration of species P there, along with the kinetic parameters. Now you might notice that this is yellow here because we haven't yet defined our Gaussian pulse. So what COMSOL will do is if there's something which it doesn't recognize, it will highlight that in yellow text generally. So we'll now define our Gaussian pulse. So to do that, we can right click, select functions, Gaussian pulse, and we're going to say that this happens at 20 seconds with a standard deviation of 2. So if we just plot that, we can see what that looks like. So moving on down to our geometry, if we go back to variables, we can see that that's now gone to black text as the function's being defined. Moving on down to geometry, we can now bring in our geometry. So to save a little bit of time, I'm going to insert the sequence. So this brings the geometry in from another COMSOL model file. So just a built version of this model. So what we have here is just our geometry sequence. So building up in stages, we start with a work plane for a slice of our pillar. We then revolve the pillar to generate this 3D example, 3D shape, and then we can array the pillars in any way. And you'll notice that each of these settings panes here will have parameters in. So this allows you to then have sort of full customization of your biosensor array just by changing what these parameters values are. So with this, we then have our block to represent our fluid channel, and then we use difference to cut away the pillars themselves, because when we're simulating the physics, we're actually only interested in what's going on in the liquid domain and on the surfaces. We don't need to have the solid pillars meshed or represented because the physics of interest aren't happening there. We can then use some additional blocks to help create our symmetry planes. So with this, we'll add in a block here. Again, use difference to slice off the lower half of this section. We can then add in another block, and then again use difference to take another slice off. And with this, then we can see the geometry which we had in the slides. So if we just make that transparent as well, we can see where the pillars are. So we then move on down, and we have a few extra features here which are called selections. So selections make things a little bit easier to define within our model. So we have a selection for our inlet, a selection for our outlet, which is this boundary here, and then we have some other selections. So selections for our symmetry plane, our outer walls, and then our reacting surfaces. So this just uses what we call a box selection. So it just takes the boundaries defined within the boxes there. We can also do other types of selections as well if you want. So you can actually click the boundaries which you want to group together and give a name. So we just finalize the geometry with the form union, and then move on to defining our materials and our physics. So if we move on down to our material node here, we can add in our material from the library. So we're going to add in our water material. And now we can see that this cross is going to disappear because now we have our viscosity and density defined for our fluid flow physics. So moving to our transport diluted species, to define our transport properties, we'll just select our velocity field there from the a drop-down box for our convection, and then define our diffusion coefficient using our parameter d. We can then add in our inlet, so our inflow, selecting our inlet selection, or we can just manually click this within the graphics window as well. And then defining our concentration. So that's our variable C0 for our time-dependent concentration. We can then have our outflow, so where our fluid is leaving our system. So we just make that transparent. We can just select that there. Now on our surfaces, we're going to have a flux of species coming in and going, where it's absorbing and desorbing. So we can define that using a flux condition here. So if we just select that, our rate of P coming in, well, entering the domain from the pillars will be our desorption rate, and then the rate of P leaving our domain by absorbing onto the pillars will be adsorption rate, so we can minus that. And the boundaries which we want to apply this to are our reacting surfaces, so these boundaries here. So that defines our reactions. We just need to now define where our symmetry planes are. So most of our physics interfaces will come with a predefined symmetry condition. We can just use our selection there to select the symmetry planes a little bit quicker. So that defines our transport. So we have our inflow, our outflow, and our reactions for our bulk fluid. We now want to define our surface reactions. So these surface reactions are only happening on our reacting surfaces, so we can just select those. And now to define which reactions are happening, we can create a reactions node using our right-click menu here. So for our P, the rate at which our surface species is forming is our adds reaction, and the rate it's being removed is minus R des. And then there's also the quench reaction for the surface species, so then we have minus R quench here. And then our quenched molecule surface species is being formed by our quench at that rate here. So again, we need to define this only on our reacting surfaces, so we can select that from our selection list there, or if you wanted, you can again click the boundaries. So that defines our surface reactions. What's left to define now is just our fluid flow. So with our laminar flow, we have already our fluid properties defined from our material. We have our walls defined already. So all we need now is to specify where our inlets are, where our outlets are, and where our symmetry planes are. So we'll take the inlet and we'll select our inlet condition here. And then our velocity is given by our parameter u in, so that's 0.2 millimeters per second. Our outlet again can be defined on our outlet boundary, so we can select our selection there again if you wanted to click within the graphics window. We also want to define our symmetry plane, so using our symmetry condition here, we can then just use those selections to speed it up a little bit. So we have those now defined there. So that's all we need to do to set up our physics for our biosensor. We can then build our mesh, but I'm going to leave that for now because we're going to open a solved model to show what's going on. So we hop on over to the biosensor because it takes a few minutes to compute. We can see that we have the mesh set up here, and we also have our study defined here. So we're taking an approach of using two steps here, which is an approach we call one-way coupling. So we're first solving for the laminar flow as a steady state problem because our fluid flow properties, fluid flow and velocity field don't change in time. So we can compute that first and then pass that through to our transport and reactions, which do change in time as a sort of solution. And then that's solved, and that can be solved over our time range. So in this case, 150 seconds. And then doing the one-way coupling approach, we then save some computation because we're not having to recompute the same fluid flow variable values each time step. So what this gives us is then we can see how the concentration changes with time. So we have the time at 75 seconds there. If we went back, we can have a look at what it looks at 25 just after it's come in, and then when it's partway through, we can see where it's then interacting with our pillars, and we can also examine sort of how the surface fraction of our P on our pillars changes with time at different points within the geometry, just by using these plots as well. Okay, yep.